About half an hour late, but we will try to finish according to our usual time. This week, the lecture is about mining data streams. And we start with the motivation of this part. Essentially, in many data mining situations, we know the entire data set in advance. So previously, a large data set, we can handle that. The problem is mainly that we cannot keep all the data in the memory. So we have the big data analytics kind of problem. But today we are going to talk about stream. Stream management means that when the input rate is controlled externally, meaning that it's out from the user, it's not for any internal control. In other words, you do not have all the data. And also you don't have the data all the time. So that means that we cannot keep the data, and often the data will come and go. The data nature will be changed. For example, Google query or Baidu query, it keeps coming, and the query flavor may change. You like to keep track of the trend. Twitter and Facebook status update will also be changing. So in this situation, we can think of the data as infinitive and non-stationary. That is, the distribution changes over the time. So in this kind of situation, then we will see, give you an example. The election 2 years ago in the United States, it was Trump versus Clinton. The story goes like almost all the mass or press predicted that Hillary Clinton will win the election. Okay, but it turns out that actually it was Trump who win the election. So the situation, I think, it doesn't display well in here. If you have the notes with you, the upper diagram essentially just show to you about the negative comments in the social network about these two candidates. And the bottom part is about the positive responses. And you can see toward the end of these two diagrams, like that is before the election, actually it was clear from social network that people like Trump more than Hillary Clinton. Okay, this is just 1 week before the election. Things change very, very quickly. So this means that social network actually can give you more relevant and truthful information about people's opinion. But the data actually change only toward the end. So this is kind of the stream model that we are talking about. That means that the stream model is the model where input is usually a tuple. Tuple means that it comes with certain record, such as the user query may include user's ID, query, and also the time the query was typed. This is a query for the internet, the search engine. And they are entered at a rapid rate at one or more input ports. Also, the system cannot store the entire stream accessibly, meaning that because the volume of data is too big. You can only take a look at the data and then get the information you need, and you have to move along. So the question is that how do you make critical calculations about the stream using limited amount of memory or even secondary memory? So in next diagram, we are showing a typical situation like what we are addressing for today's lecture. That is, we have the processor where we want to have certain algorithm to process the streaming data. So this streaming data enter as a sequence of homogeneous data. For example, a sequence of integers, a sequence of alphabets, or a sequence of just simply ones or zeros. And for this processor, we are processing the data so that there are certain query we would like to be able to answer. And this query includes ad hoc queries or standing queries. Ad hoc queries may be changing queries upon user's request. Standing query may be the query which is already over there. We want to constantly know. For example, we want to constantly know what are the topics of interest right now. So these are the query that may be put in there. Another example, standing query like ones and zeros. What are the distribution of ones and zeros as the data that we are observing at this moment? So that will produce the output. At the same time, you have only limited working space or working storage in order to keep those data. Even though you have some archival storage, you may not be able to keep all the data that you have. So in other words, you can only keep limited amount of the data that you observe. So this is the problems of the data stream that we have. The types of query that we want to answer on a stream may include the following. We want to sample data from a stream. For example, we may want to construct a random sample. Because we cannot keep all the data, but we want to know the nature of the data. The easiest way today is just to sample the data. Sampling today can be very accurate if you know what to sample. But if you don't sample it properly, then your sampling result may produce incorrect values. So I will show in a moment those kind of situations. And also, we want to have query over sliding window. Sliding window means the most recent data, you can keep them, but you cannot keep all the data. The most recent data, you keep them. We call them a sliding window of the most recent time. Then, for example, we can try to calculate what are the number of items of a type of X in the last K element of the stream. I think this will be a connection problem rather than a resolution. Anyway, okay, so it looks better this way, right? So I think it's a connection. All right, then you may want to know what are the last K elements of certain type. Then you can keep those in the window, okay? But outside the window, then you cannot keep them. So the question is that how can you maintain a window to keep those representative K items? The next kind of query could be filtering of the data stream. For example, you may want to select elements with property X from the stream so that you can have a good estimation of those properties among all the data that you have. Furthermore, we may have other type of queries. For example, we can have counting distinct elements. In the stream, they may come from different kind of elements that you have. For example, we may be interested in what kind of products people are buying today, and what are the different products that people are buying. And this will relate you to counting those different elements are there in the stream you have. So the number of distinct elements in the last K elements of the stream, this K is because you have limited space that you can keep them. So you want to have a proper way of counting those distinct elements. Another example is that even though we cannot keep all the data, but we are interested in certain kind of average. For example, we can want to estimate the average or standard deviation of last K elements. So estimating moments, like average is the first moment, standard deviation is the second moment. This will tell you about the statistic of the data. Then that might be of interest. You do not need to keep all the data, but you would like to know the statistic about the data. And finally, finding frequent elements. Last time we talked about try to estimate the frequent item sets. But even streaming data, then we may want to find what are the frequent elements or even frequent item sets. So these are problems we want to solve in the data streams. Because if we can solve this problem, then we can allow certain application. For example, we can mine query streams. This means that Google or Baidu wants to know what queries are more frequently used today than yesterday. So this will capture the trend. For example, if they can capture the trend that actually Trump is winning the election than Hillary, then they can know the information ahead of the press, okay? Because people are putting searching for the query. This represents actually what they are interested in. For example, they may have query more about Trump than Hillary Clinton, and that shows that Trump actually draw more attentions, right? So things like that is like the trend of the data can be answered from mining query streams. Another application is mining click streams. Yahoo, or today is the Bing, wants to know which of its pages are getting an unusual number of hits in the past hour. Then they will know that these are the popular web pages that people are searching when the user click that particular link. We can also mine social network news feed. For example, we can look for trending topics on Twitter or Facebook. Furthermore, we may have sensor network, which is popular nowadays about IoT kind of thing. Many sensors feeding into a central controller, then you will know certain aspect. Like in Hong Kong, there will be IoT to sense about air pollution. So in certain area, air pollution may change, and you can give the proper warning. Like a previous typhoon, where they can even try to sense the water or try to see if there's too much rain and certain places that will be flooded. Today, this kind of data can be collected from IoT devices, which is sensor networks. Telephone call records, the data feeds into customer bills as well as settlements between telephone companies can give you about the habit about people making phone calls. Or the IP packets in the network can be monitored at a switch. And this will be helpful for us to do a number of things. For example, we can gather information for the optimal routing of different messages, or we can even detect denial of service attacks, which is very difficult to prevent nowadays. But if we can detect them quickly, then we can try to detect those kind of attackers and try to defer those attacks, or try to make the attackers sort of cannot do further attack. So these are all the applications that can be applied in today's different area, which was enabled by data analytics for the streaming data. So based on this motivation, we would actually like to talk to you about this number of different aspects, and I will give you different kind of algorithm. There are actually 6 of them over here, okay? But most likely, I probably can only go through the first 4 at the most, and others may just leave it for you for study after the class, okay? So these are 6 different kind of problems which will request 6 different kind of algorithm to solve them. We focus on the first 4, or we start with the first one, sampling from data stream. Sampling from data stream means the following. Because we cannot store the entire stream, we have the one obvious approach is to just store the sample. The whole stream we cannot store them. We just sample them. So we can do the following way. We can sample a fixed portion of elements. So for example, we say 1 in 10. We cannot keep all the data. So we just sample every 10 records, we just keep 1 of them. Okay, so that's one way of sampling. We call that as a sample of a fixed portion. There's another sampling technique called maintain a random sample of fixed size over a potential in infinite stream. So even the input may be infinite stream, and I have only fixed size of memory. So I just put the fixed size memory of those data of the infinite stream. Okay, so then the question becoming, how do we sample the data so that they will enter this limited amount that I can keep? Okay, so the first one is just sample the fixed portion, like 1 in 10. But the second one is just you try to fill the space that you have, okay, with the data coming in. You keep the space of the data that you have. But then when data come in, you have to decide whether the data enter the space or you don't keep it in the space. So these are the 2 ways to do sampling. The second way means that any time t, we would like to have a random sample of n elements. For all time t, each of the n elements seen so far will have equal probability of being sampled. How can we guarantee that? Okay, so we will do this too in more detail in the next few slides. So these two kind of question. First one is sampling a fixed portion, and second one is sampling with a limited space. Let's look at the first one. So the first one, the problem is sampling a fixed portion. That means that we, for example, search engine may have a query stream, and the query stream may have a tuple. We use this as an example as an illustration about a good algorithm versus a bad algorithm. Okay, so in this example, user type in the query. So if you are in a search engine and you study about the query may come in the user ID. The query, enter the query like today's weather or Hong Kong tourist. These are kind of query terms. And then will be the time that user enter the query. So answer with question would be something like, how often did the user run the same query on 2 different days? How often would a query be entered by a user in 2 different days? This kind of question will be of interest to us because we like to know whether when a query was duplicated, that means that that particular user is interested in that query, so that can refer to that you can sell product to that particular user, for example, because he entered it twice. Sometimes people enter the query once and do not enter it again, then it may be not of interest to that user. Okay, so distinguish whether query occur once or query occur twice will be a question. Twice or more will be an interesting question. Let's just make it simple as a query happened once or query happened 2 times. But there are so many queries from so many users, right? So how can you find out which are those queries that can be answered twice by a particular user? So let's assume that we have only space to store 1/10 of the query stream. Let's assume that you have a very long query, but you have enough memory or storage to keep this query. And in the query, you would like to answer a question: how many of the query among those queries that occur, how many occur 2 times, comparing with all the query of a particular user? Okay, then a naive solution, which is not a good solution, by the way. A naive solution is we generate random integer from 0 to 9 for each query, right? Even there's a lot of query, but we only store the query if the integer is 0. Otherwise, we discard the query. So in that way, we will sample. This is sample fixed proportion. We sample 10% of the query and keep them because we do have 10% of the space of the query that we can keep in our space. Okay, this is a naive solution. So we keep all these queries, and then we can try to answer the question: what fraction of query by averaging an average user, by average a particular user, will be duplicates, right? So we can do something like that, right? We sample all the query. We have 10% of all the query that we can keep. So we just randomly sample 10%. Use a mod function, divide by 9, and then if the mod result is 0, then we keep it. Otherwise, we throw it away. This is sort of the way of mod by 10, I should say. This is sort of a simple sampling. Okay. So, do you see any problem about this kind of sampling? Again, the question is, we would like to count for a particular user of the query that he issued. There will be query appear once or query appear 2 or more times. Let's assume that we just calculate query appear 2 times. So of all the query sample from a particular user, how many or what's the portion of a query is duplicate query or query happen twice? So we like to know the percentage of that. Right? It's a very, very simple kind of question. this naive solution will have a problem. Okay, it will have a problem, right? This is because suppose each user issue S queries once. S represents single query occur once, and D query means double query appear twice. So totally there will be S plus 2D queries. Okay, and if the sample, we try to sample, the sample rate is P. Imagine P is 10% in our example over here. Then the correct answer for all the query of a user, what would be the double query? Correct answer would be D divided by S plus D, right? There will be D query or double query. Total number of query is S plus D, where S is the single query, number of single query, and D is the number of the double query. So this is a correct answer. But if we sample the way I talk about, we random sample only 10%, and P is that, say P equal to 0.1, 10%. Okay? This kind of sampling, make a guess. Will you overestimate the correct answer, or will you underestimate the correct answer? You won't get the correct answer. Are you making overestimation or underestimation? Is my question clear to you? Are you making overestimation or underestimation? Who thinks that you are overestimating this double query among all the queries? Raise your hand. You are overestimating that. Who thinks you are underestimating that? Raise your hand, please. Okay, there are more hands raised for underestimating, and in fact, that's the correct answer. Let me show you why. If we sample the way we said, sample will contain this P portion, S times P, on the singleton queries, right? Because you sample 10%, so 10% of the single query, you will sample them. They are single query anyway. But for the double query, the duplicate query, 2DP will be sampled, okay? Because there are 2 times of that double query. However, only the DP square pairs are duplicate. In other words, you might sample duplicate query only once. They appear duplicate times, but you may sample only once. When you sample the P duplicate query, you have to both times sample the type query of that particular user. Only DP square pairs are the duplicate that enter your sample. Because DP square is P times D, that is, you sample this query with probability P, so you got it. And then with another probability P, you got it again. You enter your sample twice, and then you can record it. But you have those deep duplicate query that only appear once, which is P times 1 minus P times D. P means you sample it. 1 minus P means you didn't sample it for that duplicate query. And that can appear, you sample the first, not sample the second, or didn't sample the first time and sample it the second time. So this number, 2P times 1 minus P times D, is this number. So your estimation will actually come out to be those total sample, which is on the bottom. SP is the single query that you sample it, S times P. DP square is the double query. You sample it twice, and indeed become twice equal sample, DP square. But you also have the double query, which only appear once. That's why you have 2 times P times 1 minus P as the denominator. So these are the total query that you sample. But only those DP square will be your nominator. because that's a double query. You indeed sample it twice, and that actually become underestimation. So let me give you an example, a concrete example. If the query stream is 1, 2, 3, 4, 5, 6, 7, 7, 8, 8, right? As simple as just there are 10 queries. We use an identifier to represent that. And if we sample 50% of the query, that is, we just keep half of them, the correct answer is that you have 7 and 8 are double queries. 1 through 6 are single queries. But they are totally different kind of query. There are 8 of them. So 6 of them are single queries, 1 through 6, because they only appear once. And 2 of them are double query, 7 and 8, they appear twice. Only 7 and 8 are the double query. So your percentage of the query, which is a double query, is 2 divided by 6 plus 2, which is 25%. This is the actual result based on the data. Okay? But if our sample is only keep 5 of them. Now, if you sample 1, 2, 3, 4, 5, then your answer becomes 0%. However, if your sample is 6, 7, 7, 8, 8, then it becomes 67% to be double query of all those queries, right? Because in this second example, you sampled 3 kinds of query. 2 of them are double query, 7 and 8 are double query, right? But the actual estimation, if you do this randomly, using this kind of a naive approach, what is the expectation of the fraction of duplicate if we use this sample-based method? If we plug in the previous diagram, this formula over here, this is the actual calculation. If you do this as the real sampling, it's only 1/9. The correct answer is 1/4. But your sampling using this technique actually become underestimation of the double queries. It's 1/9. So you know this kind of approach is not good, right? So what would be the solution, you think? In this situation, how would you sample so that you can get the correct answer? The naive approach we talk about right now is just for all the query coming in, I take 10%, I randomly sample 10%, right? But it causes this kind of underestimation of the double query situation. How can we make it work? How can you make it work? So think about how come it didn't work. How come it didn't work? It's because that a particular user's double query didn't enter twice, right? So how do you solve the question like that? Who has any thought? How do you solve a question so that you can guarantee the particular user's query is double query, it doesn't enter just once? Because double query should count it as a double query. But if you enter your sample only once, then in your sample, you only see that as a single query. That's why you have this kind of underestimation of the double query, right? So how can you resolve it? How can you resolve it? Well, think about just sample users. If you sample 10% of the user, and once you sample a particular user, all his or her query will enter into the sample. That will solve the problem. Is that clear to you? Because you don't sample random all the queries. You sample users and pick 10% of the user and enter all the query that user issues. Then if the query was issued twice by that particular user, then you have all the queries, right? Okay, so this kind of idea is very important. That solution is sample users. Actually, if I ask you a question, you just see the next page and then you know the answer, okay? And try to answer to me. Pick 1/10 of the user and take their search in the sample. We can just use a hash function to hash the user name or the user ID uniformly into 10 buckets, right? So instead of sample randomly of the query, you sample randomly of the users. Okay, once you see the user, you sample random user and pick 10% of the user, and once this 10% of user, you will keep all the query of this user. So in that way, we can generalize it to pick one disk of user, and we just need deep bucket. And in this way, we simply using the more function, we can do this kind of sampling to do that. And you can see the key is the following. We actually need to sample according to certain key associated with the tuple or with the record. So key means that it's a subset of each tuple's components. For example, in a tuple that we have include user's ID, the search query, and the time. The key will be the user. That key as a user will give you the major component to represent the data. So if you sample according to the key, then you will have a better representation of the data instead of random sample of all the data. And choice of the key will depend upon different kind of application. Okay, but in general, we can get a sample of any size, A divided by B. Okay, this is A divided by B, A less than B, then that means that we sample a fraction. So this is easily done by we hash each tuple's key uniformly into B buckets, and we pick the tuple of each hash value and most A. So we hash into those and B bucket and only take A out of them. So this is a way that we can easily sample a fraction of A divided by B for all the data that we have. Okay, and this kind of technique we talked about already last week when we try to do a proper kind of thing, and just use a more function, for example. And this actually will be used often in this class. So when we say sample of a particular size, okay, a fraction or something, that can be easily done by an approach like that. Okay, so this is our first sampling kind of technique, meaning that we sample a fixed portion. Any question before I continue? Is that okay? All right. Now the second one is we can sample based on the fixed size, right? Because we have fixed memory, for example, we sample according to that particular size. So the second problem is fixed size sample. So suppose we need to maintain a sample of S of the size lowercase s, and lowercase s is fixed. For example, lowercase s is maybe 10 items. Out of capital S is 100 space. That means that we have total number of data is 100 capital S, but our memory can only keep lowercase of s. This may be main memory kind of constraint. Okay, so we have this situation, then we can only keep fixed size sample of all the data that we have. And why is that the case? Because we don't know the length of the string in advance. We don't know how much data, what will be this capital S. In fact, this string can be infinitive, right? This S actually can be infinitive. So suppose that at time t, we have seen n items. Try to keep a sample of small lowercase of the items that in our sample that we have. We want to ensure each item is in the sample with the probability of lowercase of s, which is the safe space that you have, divided by n, which is the number of items that you have seen. So this is sort of the general thing we want to do. So if I can guarantee, we have lowercase of s, which is in our space to keep the sample, because that's all the data that we can keep. But for the data that we have seen, the data we have seen is this n can be changing. If we can guarantee that for any data, it has the probability of s divided by n to enter our sample, and every item has that same probability, then I have successfully sampled, no matter how much data is, I have successfully sampled them, because every item has the same probability s divided by n to enter my space. Okay? If we can guarantee every item that coming in the stream has the same probability s divided by n. S is because that's the largest space I can keep. N is the number of items I have seen so far. So if every item has same probability of being sampled or being kept in my space, that is S divided by N, then this is a correct sampling. Is that clear to you? Because I sample it, so all the item has the same probability of being sampled into my space. Because my space is S, and this N is the number of items I've seen so far. Alright, is that clear? So the question is, can we guarantee that? The answer then is yes, we can do that. And here is the algorithm for the solution. Fixed size sample, the algorithm is we can store all the first elements of the string to S. So first S element, we just store it. There's no problem, right? Because we have that much space to keep the items. So all the items in the first 1 to lowercase s, we sample them. So everybody will be sampled. Okay? That's no problem because I do have that space. So difficult problem is, what if there's new item enter and your memory is already filled up? Memory space is lowercase, it's already filled up. So this algorithm says the following. Suppose we have seen n elements, and now the n plus 1th element have entered, and n is bigger than s, meaning that we cannot keep all the items. We have to start throwing out items, or we have to decide whether an item will enter our memory or not. Then we do the following algorithm. With probability of lowercase divided by n plus 1, we pick this new n plus 1th element. This new element come in, we pick it and put it into our memory. Otherwise means that with a probability of 1 minus s divided by n plus 1, we will throw it away. Meaning that the original sample will still keep them. If we pick the n plus 1th element, meaning that this element will enter our memory space, then it will replace one of the s, which is our memory space size. One of this s element in those sample capital S that we have, we randomly pick one of them uniformly. In other words, all the item in the lowercase s space has the same probability of being thrown out and replaced by this n plus 1 element that we decide to store. Okay? So let me ask you, in those elements that will be replaced, what is the probability that an element will be replaced? What's the probability? Thank you. 1 divided by s. Every item has the same probability. Okay? Alright, so that's the algorithm. In other words, let me repeat the algorithm. When a new item comes in, if you already have no space, that is, when n plus 1 item comes in, and n is already bigger than s, then we have to decide whether this new item will sample that or not. So with probability of s, which is the memory space, divided by n plus 1. N is the number of items that you have seen. It keeps growing. Okay? N keeps growing, s is fixed. So with this probability s divided by n plus 1, then this new item we will put into our space. Otherwise, we don't sample it. So if we don't sample it, means that the original item in our sample, they are all safe, will be replaced. But if a new item that we select to replace, that is with this probability, then one of the items will be replaced. And that probability is 1 divided by S. Everybody has that same probability. So with that, we claim this algorithm maintains a sample of capital S, no matter how large is this capital S, with the desired property. That is, each item has the same equal probability to be maintained in our memory, whose size is only lowercase of s. So this algorithm or claim will work for this delighted property that we want to have. Okay? So the remainder is we prove it. Okay? Let me go through this proof because this can be proved by induction. We prove this by induction. We first assume that after n element, the sample contains each element seen so far is probability of s divided by n. So let's assume that so far, because when this initial element go from 1 to lowercase s, then we will fill up the memory. So that's not a problem. So it's only when n is bigger than s, okay, whether that algorithm will maintain the property or not. So proof by induction means that assume this property holds up to n elements. That is, up to n elements, every item has the equal same probability of being sampled. Okay? What's the probability of being sampled, by the way? Up to n elements, what's the probability that every item will have the same probability to be sampled? What's the probability? I'm sorry? Thank you. S divided by n. Lowercase s divided by n. Everybody has the same probability. So we want to prove that for the next item, n plus 1, seeing the next item, okay, this algorithm we just talked about will maintain every item has s divided by n plus 1 probability of being sampled. Because now your item become n plus 1. Okay, we want to prove that. So obviously, we see that when n equal to s element in the sample, this is what we want. Okay, so when this n is from 1 to s, that's not a problem because everybody will be sampled. Everybody is 1. So the situation is only when n is bigger than s. What will happen, right? So the proof goes like that. After n elements, the sample in capital S contain each element so far will have a probability of s divided by n. All right. Now the element n plus 1 arrive. So when n plus 1 arrive, for element already in S, what's the probability of remaining in S, remaining in our sample? Then that is that this part, meaning that the new sample will not be picked. New sample will not be picked. It's 1 minus s divided by n plus 1. Remember our algorithm is with the probability of s divided by n plus 1, that sample will be picked. So 1 minus that probability, that sample won't be picked. Then you are safe. You won't be thrown away when you are already in the S memory. Okay? But with the other probability, s divided by n plus 1, then one of the items need to be replaced. What's the probability of not to be replaced? You have the probability s minus 1 divided by s that you won't be replaced because only one of s will be replaced. So 1 minus that, everybody else will be safe. So this condition is that that new item won't be sampled. This condition is that the new item is sampled, but you are not being replaced. Okay? So this is the probability of you are still remaining into that space, right? So this become this value n divided by n plus 1. So this elements already in S, probability of remaining is this value, which is very large, right? So after time of n samples, then we have the probability of S divided by n. So this value n divided by n plus 1, when we hold this n, when n become n plus 1, there will be a probability at s plus 1. S divided by n is a probability that you may be sampled and n divided by n plus 1 will be the probability that you will not be replaced. So you are still being sampled is s divided by n plus 1 with this times this. So this proves that the item which come in, we use the s divided by n plus 1, this value, to sample that. And for all the items remain in the space, everybody also have this probability of still being sampled. Okay? So given that when before n plus 1 item comes in, everybody has a probability of being sampled as s divided by n. When n plus 1 item comes in, now every item in a memory also have the probability, the same probability of s divided by n plus 1 that will remain in the sample. So that completes the proof. Okay? Given the condition that n item, everybody has s divided by n to be sampled. After that n plus 1 item, then every item also maintain the s divided by n plus 1 the probability of being sampled, including those in the memory and the one that will enter the memory, the n plus 1 item which will enter in the memory. That's completion of the proof. Okay, so if any question about this, by the way? This is a standard proof by induction, okay, for this particular problem. Is that okay with you? All right, I actually do not need to go through the proof in this much detail, just let you know the algorithm. But the algorithm actually was designed so that it can guarantee this situation we just talked about. That is, all the items that come in, we have the same probability of sample that into our memory, where the memory size is lowercase of s, and the total sample, the total item that coming in the string may be capital S, which is a growing number. Okay, and we use n to represent the number of items that comes in. Okay, and this algorithm will work for all the items have the same probability of being sampled. Okay. All right, let me get to the next question and also the algorithm. The next question that we would like to address is try to query over a long sliding window. This is the situation where, again, we have initial number of data coming into the stream, right? And we like to know some kind of the property of the stream. And usually we keep the most recent data of the stream that we have. How do we keep that? The question is, how can we keep those data? Because we have limited space to keep those data, and we call that as a window of the time to keep the data. So these are the query over a long sliding window kind of question. So we define the idea of sliding windows. Sliding windows is a useful model of stream processing, where the query are about a window of a fixed length, capital N. The N is the most recent elements that's received. So even though you cannot keep all the elements that you have seen, at least you can keep the most recent N. Okay? So this most recent N, then we call this a window size of N. The interesting case is that N is so large that it cannot be stored in memory or on the disk. Okay? The most recent N window, we cannot keep all of them in the memory. And it could be because N are keeping the item, data about the item. Okay? And we may not have that large number of N. N can be a trillion. Okay? You may not have that large window to keep that. Or there may be many streams you need to keep. Even though you have a very powerful computer with a lot of memory, but you may want to keep multiple streams of the windows. You may want to keep data about different products. You may have a million products. Every product you want to find out what are the property of that product when they come in as a stream of the data. Okay, then like people search for that product or has some kind of information about product, and that stream may extended to 1 million streams. So even though you have a powerful memory with a lot of powerful computer with a lot of memory, you still have a fixed window size that you can keep. Okay, so this kind of assumption, n is so large that it cannot be stored in memory, is a realistic kind of problem. Right. So let me give you a sliding window kind of example. For example, we may have a stream of this. The time goes from left to right. So this is data m that we have seen in the very early, and then we see data n. Let's assume that this is a stream of letters. So we see letter M and then letter N and B and C and X and Z, L, K, J. Okay, and now you assume that you have a window of 6, meaning that you can only keep 6 alphabets, all right, 6 letters. Then the current most recent 6 is this 6. That is 6 time slots ago you saw H and you saw G, you saw F, you saw D, and you saw S, and you saw S. So the time is going along. Okay. So I should say that the path is left. So it should be the other way around. This is the path Q, W, E, R, T. You have seen before. And then the 6 time slot before you saw A, and then you saw S and D, F. Because these are the past. Now these are the future. So this is the current time. And the future you may see J, K, L, Z, so on and so forth. So sliding window means that you can only keep a fixed size of the data. So this window you saw, you keep it as A, S, D, F, G, H. Okay? And then the next time stamp, then J comes in. And you have to throw A away because you keep the most recent 6 items. Okay, and then the next item comes in, K, you keep it, and early item you throw away, and then next item coming, early item you throw away. So these are the ideal sliding window. Okay, sliding window is important because it keeps the most relevant data up to now, because usually the most recent item are of more interest. Like if you keep track of search query, then you may want to keep track of search query of today rather than 10 years ago, because today's query represent what is happening right now, right? So the idea of sliding window is a way that we can sample among large amount of data. The question, however, is that this n in this example is 6, but in real case is that the n may be even too large to fit into your memory. And you want to keep this n. How can you make it done properly? Let's use a simplest example. Because your string can be string of letters, can be string of query or other things, right? Let's just make a simple as a stream of bits. Okay? So the problem is that we're given a stream of only zeros and ones, and we want to be prepared to answer the query of the form. How many ones are there in the last k bits we have seen, where this k is less than or equal to n. N is the window, okay, can be up to n. So the last k, how many bits are ones and how many bits are zeros? So this is already the simplest question. We just want to count bits, count the number of them. This is simplest kind of the statistical you can do. Of course, in realistic problems, you can do more complicated. But even in this simple one, we want to find the solutions to this. And the solution has to begin in a situation that the n is larger than what you can keep. So large that you cannot keep the whole n, capital N. Okay, one obvious solution is that we can store the most recent n bits, capital N bits, right? That is, when a new bit comes in, we discuss the oldest n plus 1 bit. Okay, this is one way we can try. Okay, but the question is that we cannot get get an exact answer without storing the entire window, the entire n. If we cannot store the entire capital N, then we may not be able to have an accurate estimation of even number of ones in the bits string that we have. Okay, but the real problem is, what if we cannot afford to store this n bits? Okay, for example, we are processing 1 billion streams, and this capital N is 1 billion. We have 1 billion stream of different kind of information that we have. All these are all Boolean stream, but represent different kind of data. Okay, and if you use n equal to 1 billion, 1 billion times 1 billion is already that your memory cannot fit it. Okay, so this n is something that could be limited, but we are happy to have an approximation. Even this n is a big number, we cannot keep them, but we like to be able to approximate it. Okay, so get back to this. Our attempt is how many ones are there in the last capital N bits. And a simple solution that we can have, which does not solve our problem, is we can assume uniform assumption. If we assume that the number of bits were coming in uniformly, then what would be the solution you will say? If the number of ones is among all those bits are uniform distribution, how do you do the calculation? You just do a statistic, right? Anyway, you can just maintain 2 counters, okay? And S counter count number of ones so far, and Z counter count number of zeros so far. S is a single, Z is 0, right? Then how many ones are there in the last n bits? Easy. N times S divided by S plus Z. Because S divided by S plus Z is a probability that you will have the bits is 1, right? Then times n is last n bits, the number of ones, you can easily calculate that. Okay, but this is not the solution we want, because this assumes uniform distribution of the 0 and 1s. But in reality, 0 and 1s will change their distribution. And in fact, that's the reason why we have the sliding window. We want to know what are the most recent n bits, what is the distribution, because that distribution may change. So this is a solution that we want to solve. What if the string is uniform? That is, the distribution will change over the time. Okay, so we cannot use this solution. We have to use a solution that we faithfully keep counting the bits that appear in the most n window size. Okay, but unfortunately, we cannot keep this capital N as the whole window. So what do? Here's the algorithm that I'd like you to know about in more detail, and this is called DGIM method. It comes from 4 authors. This is the last name of the 4 authors, and their first letter of their last name is DGIM. That's why it's called DGIM method, right? By the way, if you invent a method that comes to a textbook, and your name may appear in that method as well. And this method do the following. We do not count exact the number of the bits in the past capital N window, okay? But we can have an estimation of that. We cannot store the total n bits, but we can estimate that. And that estimation is we only need to store order of log n times log n. Log n times log n is log square n. Okay, you should know this notation. Okay, this is log n times log n is log square n. By the way, this is high school mathematics. We store only this bits per string. In other words, the amount of the memory that we need to keep in order to store data is very, very efficient. Okay, because even n is very big. Log n become very small. And log n times log n won't be too big either. Okay, so this algorithm only need to use that many bits to store your data regarding counting of ones or counting of zero in your window size of n, that is in the past n bits. However, it gives an approximate answer. It guarantees that the worst situation is that you are off by 50%, error by 50%. Now you may say that 50% error may be too big, okay? But this is a worst case scenario. It guarantees that this is the worst case scenario. And most of the case that it may not be that bad, okay? So that's the guarantee that here it has. The error factor can be reduced to any fraction bigger than 0 with more complicated algorithm and proportionally more stored bits. In fact, this can be modified that it can reduce to not just 1/2 error, but 1/4 or 1 divided by n. If you n is 10, then error becomes 10%. Okay, but let me introduce this to you as an error 50%, and it can be extended with more stored bits and with more complicated algorithm. This error can be reduced. Okay, but we start with simplest algorithm where you only require that many bits to be stored, and then error is guaranteed to be its upper bound of error is only 50%. That is no more than 50%. All right. So how does it work? I will explain to you in the following slide. But the starting idea is the following. You want to count the bits in the n window, and you don't have that n to count it properly. Okay. How do you maintain the counts? An idea is try to maintain the counts in an exponential increasing kind of size. And we call that as exponential windows. The idea of exponential window where the solution that doesn't quite work is the following. We can summarize exponentially increasing regions of the stream looking backward into the history. Okay? And we drop small regions if they begin at the same point as a large region. You use the property that the small region in the power of 2 to the power of r, for example, region of the size of 2 to the power of 1, which is 2, region of the size of 2 to the power of 2, which is 4, region of size of 2 to the power of 3, which is 8. Growing in that kind of size, you will have exponential growth of the size. Then we can estimate the bits in each region, and in that way, we do not need to use that many bits to represent each region, as well as the bits in that region. That was the idea called exponential windows. To explain this better, I use the diagram to show that. So this is the history. This is history, okay? This is what you can keep. And the future, now the future is on the left, and the past is on the right, okay? So assume that your n window is this capital N. The bit string go from, you have seen 0, okay? And then you have seen 1, you have seen 0, and 1, 1, 0, 0, so on and so forth, until the most recent one. Now, this is the current time over here, because your window cannot fit all the n here. So you have to sort of limit to certain. Then, how do you keep track of the data, the ones you have seen? You use the window size of 1, then first window size of 1 sees a 0. The second size of window of 1 sees a bit of 1. You recall that. Then you start to recall window of size 2, 2 to the power of r, by the way, 2 to the power of some number. And window of size 2, this is window of size 2, you see 1 once. This is your window of size 2, you see 2 ones here. Okay? And now you start to have window of size 4. Window of size 4 here, you see 2 ones. Okay, window size is this 4 bits here, you see 2 ones. And window size, this is also window size 4, you see 3 ones here. So that is a record of 3. You have window of size, next window of size 4. Okay, this window of size, window of size 8. This is window of size 4. This is window of size 8. It's always multiplied by power of 2. Then you see 4 ones because there's 1 here, 1 here, 1 here, and 1 here. So you recall this 4 here. And next size is the window of size 16. Right? So this window of size 16, you have seen 10 ones in this blue region over here. Okay? And then the next window of size 16, there are 6 ones over here, but you cannot see that long. Okay? You cannot see that long because you may just end up something here because n is quite large. You want to keep up to n here. You want to keep up to n over here, but you have only complete record of 10. You do not have complete record of 6 because this is outside the window of n range. All right? This n is a number that you say you want to keep that window size of data. You can keep all the data up to this, but in the future you haven't seen it yet. Right? But you can recall them. So the idea is that we can construct the count of the last n bits up to last this n bits, except we are not sure how many of the last 6 are included. We can guarantee that what we have seen, window of size 1, window of size 2, window of size 4, and window of size 8, window of size 16, which up to this we can fully count. But the next window of size 16, okay, we only have seen 1, 2, 3. We don't see all the 6 bits because these are in the future. So we have to estimate this last one. Okay, so the thing is then, why are we doing this? I will explain in that moment. The reason why we are doing window of size 1, 2, 4, 8 is because we can combine the window. 2 windows of size 1 combined together become 1 window of size 2. 2 windows of size 2 combined together become 1 window of size 4. 2 windows of size 4 combined together becomes 1 window of size 8. So this is where the explanation window can be formed. And also this also the way that we record this window, because they are the size of 2 to the power of r, then the way to record them, we only need to use log n, where n is the window of size, in order to record that. So we do not need to use the capital N to record it. We can use log of that. Okay, so this we can need to store log n bit to represent each window size, another log n bit to represent how many ones are in that window size. Okay, that explains why log n times log n, that much space is needed. Only that much space is needed to keep track of this window of size n. Okay, all the log n counts of log n bits each. Okay, and easy to update a small bits enter. This algorithm has an advantage that when one bit enter, okay, when 1 bit enter, depends on whether it's 0 or 1s, then you can form window of size 1 and decide other windows size which should be updated or not. But in any case, for each of them, you just need log n to represent the window. This is because the window size is always size of 1, 2, 4, 8, so on and so forth, right? So you just need to use log n to represent that window, because your log n has a power to express size of 2 to the power of n. Log n can represent size of 2 to the power of n because the size is fixed in that sense. Okay, and then another log n just count how many bits are there to represent it. Okay, but there is a problem with this algorithm, is that the error in the count no greater than the number of ones in the unknown area might cause of the problem. So let me explain what's not so good for this algorithm, and then I will explain the correct algorithm and in detail, you will know how window of size 2 to the power of r can be formed to the next window. Okay, so what's not so good? As long as the ones are fairly evenly distributed, the error ratio due to the unknown region is rather small, no more than 50%. Okay, but this is only assuming that distribution of the data is even enough. But in reality, this may not be the case because data are changing. You cannot guarantee the distribution of the data. If it could be that all the ones are in the unknown area, at the end, you may have estimation of the error which is unbounded. That is, 100,000% of error. Okay, estimation error can be unbounded. Why is that? We can look at the example that we have right here. Okay, now assume that you using this to count. In this example, okay, you can correct counting all these ones up to this region, and then for the next region, because it's window of size 16, you may need to estimate the number. Okay, so your estimation, you have to base on estimation. Now, if unfortunately what you have seen in the current window are all 0, so let's assume this 0, 0, 0, all are 0. Okay, all are 0 up to here. Okay, and you will say that now with a window of size n, they are all zeros. The most recent one are all zeros. Okay, that's what you have seen in your data. But it could be the situation that the ones are all here. Here are all become ones. So in fact, the count of recent data that you have seen doesn't encounter those ones. You only estimate, and based on your estimation, you only see zeros. But in fact, there are some ones. You estimate there's no ones, but there are some ones. The error is already infinitive. Error rate is already infinitive. Okay? So this has a situation that because your window size did not get into the situation, what if there's no ones you have seen, but the ones you haven't seen is still coming out there. Okay? So as a result, the DGIM algorithm will not use the window of the size for each of the position, but instead using the window that is counting the ones. That is, you count appearance of ones. You guarantee that counted number, the ones, you will count them. Okay? So the algorithm goes like the following. The fix-up algorithm, instead of summarizing a fixed length of blocks to count whether there are 0, how many ones are there, with a specific number, we will summarize blocks with specific number of ones. And in fact, this specific number of ones is again to the power of something, to the power of r. We want to count the block of 1 ones, 2 ones, 4 ones, okay, 8 ones, 16 ones, so on and so forth. So it's exponential number of ones to the power of n. So we can let the block size, that is number of ones, increase exponentially accordingly. And the advantage then also is that the memory, the way to recall those size can be a small number, just log n, because you just need to recall of various size 2 to the power of r, only that r, and as a result you can recall using log kind of bits to keep track of that, similar to the previous algorithm. But when there are new ones coming to the window, the block stays small, so errors are small. Okay? Even if the largest block you have estimation, the error can be bounded. So the algorithm goes like the following. Each bit in the string will have a time span starting from 1, 2, 3, 4, so on and so forth, until the capital N, because N is the window size you want to keep. So you can use timestamp to represent them, but because your window size is only up to N, you can record the timestamp as a modular n, because outside that you can reuse the initial. So you count 1 to n as a timestamp, but then after n you can count back to 1. So that the mod n will still give you the proper timestamp accordingly, because this is the size n is what you are interested in. So we can represent any relevant timestamp using only log 2 to the power of n bits. We don't need to use n bits. We cannot afford to use n bits because n is a size we cannot keep. N is too large. But log 2 n bits we can keep, because again this is due to the exponential size of the window. Our timestamp recorded window is only of exponential size 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, so on and so forth. Okay, so log 2n can represent those different timestamps. Okay, and we use the buckets in the DGIM method as a record which consists of the timestamp of the end of the bucket, which is the sort of the end of the bucket means that the most recent record about that particular bucket of that size, and that will only need log n bits, not n bits, log n bits. This is because again the size is 2 to the power of some number, okay, exponential, and the number of ones between its beginning and ending is even easier to give, because the number of ones in between beginning and ending is only either 1 or 2 or 4 or 8. So we only need log n. That is, log n is just the different size. But log n can represent, because there are only either 1 ones, 2 ones, or 4 ones, or 8 ones. That's also the log of that we keep to represent the beginning and end of that window. So we essentially just need log n bits to keep track of the window, and then there are log n of them. That's all. This is an even smaller number regarding what's the size of that particular sort of window. Okay, because it's only window of size 1 or 2 or 4, so on and so forth, right? So the constraint on the bucket is number of ones must be a power of 2, and that will explain this log n here. Okay. And this algorithm goes like the following. We represent a string by this bucket, either 1 or 2 buckets with the same power of 2 number of ones. So the power of 2 number of ones, the number of bucket is either just 1 or 2, no more than 3. Okay? Because if you have more than 3, we can start to combine bucket size smaller to a bucket size larger, because they are all power of 2 to the power of n. Right? So bucket do not over on the timestamp. Each bucket timestamp are separated. This also can be done. And bucket are sorted by size from the lowest one to the highest one in that order. So earlier bucket are not smaller than the later bucket. Okay, earlier bucket are not smaller than later buckets, so that we can guarantee when we scan through the bucket, we know we can expect and calculate the size accordingly. And finally, buckets disappear when their n time is bigger than n time units in the past, because our interest is just keep the most recent n bits. If they are beyond the n bits, then we do not need to keep them. Okay. So these are a bit maybe wordy. Let me just explain that. These are the things that was putting down here. But let me explain it in. I'm sorry, this diagram has disappeared. Sorry, the diagram. You have the diagram in your handout over there, right? So you can see in your handout in the diagram. Again, I think this is a projector's problem, that the diagram disappears. In your handout, in the diagram that you have, you will see the situation of the following. Your situation that on the right hand side, you see 2 of 1s, 2 of size 1, because size of a bucket grows exponentially from size of 1, size of 2, size of 4, size of 8, and then size of 16. But the size of 16 partially are beyond the window. For the size of 1, you see 2 of them as the size of 1. Right? You see 2 of those are the size of 1. So you easily count there. You have seen 2 1s. Okay? And you see that 1 size of 2. Then you also see another 2 1s. This time because the bucket size is 1. Then next one is 2 of size 4. So you see 8 1s. And you have 2 of size 8. So you see 16 1s. And the last bucket on the left hand side, then it's outside the window end already. But you can do estimate because you have seen that it's a 1 bucket size of 16. But it's not, it's just entering with 4 1s over there. You have to estimate what will be coming over there. Okay, so here then with this bucket size, you can calculate once because you just do 2 times 1 plus 1 times 2 plus 2 times 4 plus 2 times 8. And the last one you have to estimate it. But the first few you have exact calculation because each bucket you count the number of ones. And number of ones is what you're interested. You can count them correctly and properly as a result. Okay? So this is when you count the results as a final thing. But the question is, what if a new data enters? How do you update those different buckets? That's the difficult part. Because counting the number of ones or estimating number of ones is just done by this directly calculating that. But updating is the difficult part. So let's see how do we update the buckets. Update the bucket is that when a new bit comes in, then we will drop the last or the oldest bucket if the end time is prior to end time units before the current time. So it meaning that if the last bucket drop out of your end window, that is not of your record you need to keep anyway. You will drop it when a new bit comes in. So there are 2 cases though. The current coming bit is either 0 or 1. If the current bit is 0, no other changes are needed. You don't need to do anything. Why is that? If a new bit is 0, you don't need to do anything. Why? Because it doesn't change anything. Our algorithm is counting the bit of ones, right? And your record, the window size is sized when there's ones coming, then you will change the bucket size accordingly. So when a new window come in, only when this end will be increased, only when the oldest bit drop out, the oldest window drop out of this total end window, okay, then you update that. Otherwise, you don't need to change anything. So the interesting part is only when the bit comes in is 1. Okay, so this is a complicated part. So if the current bit comes in is 1, you create a new bucket of size 1, right? The most recent bucket is a smaller size. So this bit must be 1 by itself. You create bit of 1 for just this bit, and the end of timestamp is that current time. That represents that this is sort of the boundary of this block. Okay? Then you have to start looking at the current number of buckets with size of 1. If there are already 2 buckets of size 1, meaning that there are now 3 buckets of size 1, then you combine the oldest 2 into the bucket of size 2. Because we are using the expression bucket size of exponential. So lower bucket size can always be combined together to form the next larger bucket. Because 2 to the power of 0, 1, 2, 3, 4. In this case, 3 buckets of size 1. You can keep one, the most recent one is bucket size of 1. But the 2 older bucket of size 2, 2 older bucket size of 1, you combine them together to make a new bucket of size 2. Okay? But what if you have already 2 buckets of size 2? Now you have 3 buckets of size 2. You do exactly the same thing. You combine new 2 buckets of size 2, combine the oldest 2 into the bucket of size 4, so on and so forth. Then you can keep combining that. Because the bucket size keep growing, at the end, then your bucket size can be maintained to be either 1 bucket or 2 buckets, and that's all. Okay. Next slide. Again, unfortunately, this is an empty sheet over here. But let me just explain to you how it works. The way it works is that you go from top to the bottom, and you see the history. The top one, you see there are a bucket. The right hand side here, you see 2 buckets of size 1, right? And then you see 1 size of bucket 2, and you see 2 size of bucket 4, and 2 size of bucket 8, and then 1 size of bucket 16, but it's out of the window that you want to keep already. Okay, so that's the first row. Second row, you see that a 1 comes in, right? When a 1 comes in, then it forms 1 bucket of size 1. But you already have 2 buckets of size 1. So now you have 3 buckets of size 1. You need to form the oldest 2 buckets size of 1 and form them into 1 bucket of size 2. So that you see that 1 bucket of size 2 there and 1 bucket of size 2, and other remain unchanged. Okay, that's row number 3. And row number 4 is that you have seen the new data when it is bucket of size 1 come in, is a bucket of size 1, and 1 comes in, it's bucket of size 1. So nothing changed because you have enough bucket of size 1, you just keep it bucket of size 1 until the last 1 come in. I'm talking about row number 4 here. Row number 4, you have now 3 bucket of size 1, right? You have to form the oldest 2 bucket of size 1 into 1 bucket of size 2. Okay, but in that row number 5, you see that now you have 3 bucket of size 2, so you have to form another bucket of size 4. But now you have 3 bucket of size 4. You have to keep combining them until the end. Okay, so that come out with the last row over there. So last row, at the end, you have 1 bucket of size 1, 1 bucket of size 2, 1 bucket of size 4, 1 bucket of size 8, and 1 bucket of size 16. So that's how it's updated. And the remainder will be fall out of the window N that you are interested in. But you can keep updating as a result this way, and you only need log N bits times log N bits to keep all this data. Okay, and you can do the estimation accordingly. I don't know, is it clear enough to you or not? But let's take a break, and you go to the last slide. I want you to do in-class practice as the last slide while I'm trying to fix a problem here. Okay, so I'm jumping to this the practice. So go to the practice and then see if you can do this example. So let's take a 20 minutes break, and after coming back, I will explain to you the solution to this last example, where in this in-class practice, I've shown to you that there's in-class practice 1. There are several ways to bitstream. So there are several ways for this bitstream could be partitioned into bucket, right? So try to partition it, and then I'll show the solution. If you can partition it properly, that means that you understand this algorithm. Okay? All right. Let's take a break while I'm trying to fix this projector problem. I hope I can fix the problem, hopefully. So this one, I'll give you the answer. Again, the solution will be posted on the website. So let's assume that this is a string which comes in, the same as the example given before. And we count it from right to left. Right represent the newest data, left represent the oldest data. So if this data that was in the data stream, then in our DGIM algorithm, how do we represent the different blocks? So the answer is this. You can have 2 blocks of size 1, 2 blocks of size 2, and then this block actually is out of boundary. So you recall just like that. Or you can have 2 blocks of size 1, 1 block of size 2, and then 1 block of size 4. Or 1 block of size 1, 2 block of size 2, and 1 block of size, suppose 4, but this is again fall out of the boundary. Or 1 of each, like 1 block of size 1, 1 block of size 2, 1 block of size 4, and this remain that out of the window. Okay, so this is sort of the 4 different things that can be partitioned for the data you have seen so far. Maybe I can go back to try to explain a little bit more of the previous one. Let's see if I use an arrow. Go back. Okay, and I'm going to turn on the pointer as well. So now we can see this one. So what I'm trying to say here is essentially that counting them is easy. Just the number, only 2 number ones, 1 number of 2s, 2 number of 4s, and 2 number of 8s, size of 8. So this can become easy. The thing is that how do you form them? And so the thing that we had to form them earlier, again, this to explain it again, is that if this is the original that you have, right, and then you see one block size 1 coming, then these 2 ones need to form a size of 2, and this is one size of 2, so you stop right there, it's no problem. And then you see 101 coming, because when another 1 coming, it doesn't affect the thing. Another 0 coming doesn't affect the thing much. So that's why I show when this 101 coming, then you have 3 ones here, and that's why these 2 ones need to form a block of size 2, and now you have 3 of this block of size 2, so this need to form a block of size 4, but you have 3 of block of size 4, so this 2 need to form a block of size 8. Now you have 3 of block of size 8, and that's why this is a block of size 16. So you have 1 block of size 16, 1 block of size 8, 1 block of size 4, 1 block of size 2, and 1 block of size 1. So this is just like the way it looks at the sequence. Okay, so to explain this way. And again, I do apologize that some students want to ask me questions, but you can still ask me during a break. So the thing is that how to query to estimate the number of ones in the most n bits. This is very easy. You just sum the size of all buckets, but the last one, because you will have exact count of all the size of 2 to the power of something, and you sum them together, and the last one, you just add half of the size of the last bucket to do an estimation. Okay, you estimate the last bucket because you don't see all the all of them. Remember, we don't know how many ones of the last bucket that are still in the window, but we can limit the errors that may occur. This is because that we have correctly estimated the number of ones. We don't estimate whenever we don't see ones. It doesn't affect us. So only when we see ones, we have the estimate. So the bucket size the smaller bucket size, or the most recent the bucket size of ones, we can exactly estimate that. The only one we cannot do precisely is the last bucket. Okay, but we already have enough ones that will reduce our error. Different from the previous algorithm we talked about, where you may not see any zeros. Okay, and at the ones you haven't seen that, you estimate that the number of ones is none of them, but in fact you did not estimate it correctly, because oh, I'm sorry, I better don't move. Okay, but this one will have not that kind of problem. So this bucket, we call this is a bucketized stream as a result. And earlier you may ask about a question. Now, what actually do we remember? Notice that even this n is so big that we cannot record this n. Okay, this length is so big that we do not record. We do not record this value, this whole string. We do not record it. What actually we recorded is just the timestamp of each of them, because this timestamp, that is a position where they are in n. What's the position in n? You use log n can represent the position in n. Right? This n is a long bit stream. Okay, for example, this could be 1024, but you only need to record the position in 1024. Then you only need 10 bits. 2 to the power of 10 is 1024. You only need 10 bits to point out any position in this 1024. Only log 2 to the 1024, that's 10. Only 10 bits you can record any of this timestamp. But you don't need to record all of them, because the size of that is 2 to the power of something. You don't need to record every position of this n. You only need to record those, because of bucket size, the position is 2 to the power of 1, 2, 4, and anything. So this position is just the log scale inside this n. And again, you only at most of log n bits you need to record. So totally is log n times log n. And the size of each is even smaller, log n for each of the size. So that's negligible. That's why to record all this, okay, to record all this, again, you don't even know, you cannot even record this n bit, right? This n bit to record it, you cannot record them. This n number, Windows, you cannot record all of them, but you can use log n to record the position in this n bits in order to do the estimates. All right, so the error bound, proof of error bound is like the following. I quickly explain it. Suppose the last bucket is of the size of 2 to the power of r. Okay, remember the bucket size is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, so on and so forth. The last one as the largest bucket size, that is assuming it's 2 to the power of r, right? So your error can only occur in the last bucket size, 2 to the power of r. You can have all the previous bucket size to be correctly estimated, because only ones will be forming the bucket. So assuming the worst case is that you have only each of the bucket size from 0, 1, 2, 3 to the power of 2 to the r minus 1 are only one of them each. Okay, then that's the number of ones you have already. That is 1 plus 2 plus 4 all the way to the power of r minus 1. That is the number 1 you have correctly calculated. So these are total. These are the total number that is that you have from 1 to, and only the last last one, the last bucket size of 2 to the r, you cannot correctly estimate it, right? But you have already 2 to the power of r minus 1, you estimate it correctly. And because last bucket size, the worst case is that you completely estimate. You only see 1 bit and you completely not estimated it correctly. But at least that 1 bit you get it correct. So the worst case is 2 to the power of r minus 1. These are the total number of bits. And the error ratio is this 2 to the power of r minus 1, which is the one that you may not estimate it properly. That's the most thing. But others, you can estimate it correctly. Okay, so that's why this divided by that is about 50%. You can just roughly think about that last bucket. Even you totally estimate it incorrectly, okay, you still have the first 1 to 2 to 2 to the power of 0 to 2 to the power of I minus 1. Number of ones, you get it correctly. So those ones, you add them together, is roughly the size of the last bucket in the worst scenario. That's why the error can be bounded as the 50% in the worst situation. Okay? Anyway, you can read this in more detail. There are extensions for thinking. Question, for example, is that can we use the same trick to answer the query how many ones are in the last k rather than last n, as long as k is less than n? So that can be done. You just need to do some minor modification. Also, can we handle the case where the string is not bit string, but integer string? And we want to sum, for example, the sum of the integer of the last k bits, or the last k integers. That's just also extension from counting the number of ones. Okay, you can modify this and make it work. And also, we can reduce the number of error. Roughly, now we form we use 2 to the power of r, and we can form 2 of them into one bucket. But instead of maintaining 1 and 2 of each size bucket, we can allow up to I minus 1 or r, okay, for r bigger than 2. So in other words, we can use 3 bucket, 4 bucket, 5 bucket in order to form the next one. So in that way, then we expect the larger size of the bucket to be divided. So larger size of the bucket that can be actually divided to smaller one, because the largest size bucket, the last one, is the one that we will have error. Right? The previous bucket, we won't have the error. So that will essentially reduce the error down to 1 divided by r. So our example given to you, r is 2. That's why error is at most half, 50%. But we can reduce it down to 1/3, 1/4, 1/5, so on and so forth, at the price of more complicated algorithm and more bits that we need to use in order to represent each of the bucket size and the timestamp as well. Okay, but I won't elaborate that. This is picking up appropriately. We can trade off between the number of bits and the error that we want to tolerate. Okay, the next one, I think let's get to the next one. I promised that we should be done by 5 o'clock. Sorry, that may be extended time a little bit. The last one is about filtering data streams. Okay, so this one is to see the following situation. That is, we may have each element of the data stream is a tuple, which is a finite list of the element. Okay, and let's say given a list of keys of S. Remember, we use keys to do better way of determining or filtering about different streams. That in the first example I gave you, right? We try to decide not to randomly select 10% of the search query, but we have to do 10% of the user and all the search query of that user. In that way, then using the user ID as a key, our sample may be done properly. Right? So this kind of thing, then we have the list of the keys associated with each of the data tuple. And question is, how do we determine which element of a stream have a certain key, this key tuple there, in that S? This kind of example is sort of pretty typical. And the obvious solution is use hash table. You use a hash table to hash that key, so that we can determine whether that particular sort of data will include that key or not. We don't need to compare the whole key, but we can hash it so that we can do proper checking. But suppose we do not have enough memory to store all the S in the hash table. For example, we may be processing millions of filters in the same stream. So when a string comes in, there may be many filters. We look at this stream. Then we may not even have enough memory to store all these keys, okay, in our memory. Then how do we handle the situation that we will want to filter some data and take the data as some of the things that we are interested in? Okay, so the application that this may be allowed would be like email spam filtering. So, for example, we know there's 1 billion good email addresses. So if your email address that sent out, if Google Gmail, right, and Google knows that there's 1 billion users who are legitimate users, so they have these email addresses as the key. All right, the rest of the email may be just contents of the key. So they want to use this key in order to determine whether a new email coming is not spam email. It's really come from that 1 billion good addresses. So if an email coming, okay, it is not a spam. This is one of the example. And publish subscriber is another one. But let me just use the email spamming filter as an example. Now the question is that you cannot even keep this 1 billion so-called good addresses. 1 billion addresses is a lot, right? When there's a new address coming, you want to compare with those 1 billion addresses. It's prohibitive because you couldn't even store them. So how do you handle a situation like this? So that when an email coming, you can say, there, this is a good email. Okay? You cannot keep all this key in the table. What do? There's a solution, but let's do a first cut solution. This first cut solution, this is again, okay, I thought better don't move. The first cut solution is given a set of keys S that we want to filter, okay? We cannot keep all these keys, by the way. So that's a very smart idea, is that let's create a bit array, a long bit array, okay, with n bits. But because it's a bit array with n bit, we can handle this even long bit array. Okay, this very array, initially we put all of them to be zeros. Now we have this large number of key that we want to handle. We choose a hash function h, and we say, and then we hash it. So we hash this h function. This hash function that we choose to enter essentially represent the thing. This is just hash it with 0 to n, so that this you can hash it to this n bits. That's just as easy as that. And hash each member of this. This is like the email address. You just hash this address to one of this n bucket, so that you turn on the bucket of particular bit to be 1 if the hash function of that key, hash of that key of the corresponding position in that bit array, that particular bucket. Then if you hash it to that bucket and you turn that to be 1, okay? Because hash function can hash to different position. So as long as you have a long bit array, then you will turn on different bit to be 1. But when you do the hash, any fixed key will turn on a particular position to be 1. That hash function can be done. So that's a bit position of that hash function to be 1. Okay? You can imagine that this hash function is hashed to be a range of 0 to n. Just turn on that bit of position 0 to n to be 1. Right? So this is just a straightforward hashing. And we can hash each element A of the stream and output only those hash bits that was set to 1. That is, any new address coming, we will output those only when it hash to the bit array, which is already 1. Meaning that we can have, for example, 1 billion addresses. Okay, the example go like that. We have 1 billion addresses. These are good addresses, good email addresses. Okay, we hash it to an array of 8 billion bits. When you hash to an array of 8 billion bits, you just need 8 billion, 8 gigabyte, just 8 billion bits is not just 1 gigabyte to store it, right? But then you hash this 1 billion addresses to turn on the position. There's 8 billion position. You turn on corresponding position to be 1. All right? If you're lucky enough, this 1 billion addresses turn on 1 billion of those 8 billion bit to be 1. In other words, you use that bit to represent legitimate email address. So whenever a new email address comes in, you don't need to compare with this 1 billion address. You just do this hash function, and if that corresponding bit is 1, that's legitimate. If that corresponding is 0, then that means it's a bad email. Is that clear to you? So this is the key idea. In other words, this 1 billion address you cannot keep, but you can keep this 8 billion bit array and use hash function to represent them. But this situation is like this. So you have this filter, you have a bit array, a large bit array, and when you already turn some of them to be 1, meaning that these are the good addresses which will hash those bits to be 1. So when a new item comes in, and then if it maps to a 0, okay, then it will drop the item because that's a spam mail. If this email hash to a 1, then you output that because that's a good email. Right? So in this situation, do we have false negative? Will we have false negative? We don't have false negative. False negative means that it's not a good address. It's not a good address, but you say it's a good address. Okay? If it's not a good address, then you will turn hash to a bit of 0. Okay? Of course, it's a bad address. But you may say it's a good address, but in fact it's a bad address, because you may actually happen to hash to a particular bit. If there's a bad address, actually just randomly hash one of the bit and it turned out to be 1. It can be the case. Then you say it's good, but actually it's bad. So we can create false positive. False positive means that it's good. You say it's good, but it's bad. But you won't have false negative. Okay, so this is sort of situation. If the item in S we surely output it. If not, we may still output it. A bad address, we may still thought that it's not a spam and then send it out. But the question is actually how can we estimate it more properly? All right. So the next one is that we do a more accurate estimation here. Let's use the example to represent. It's probably easier. Let's assume that there's a 1 billion email addresses. These are good email addresses. And we use 8 billion bits, a long Boolean vector to represent the hashed results. If the email address is in S, then it surely hashed to a bucket that has a bit set to 1. Right? So it always gets through. That is, there's no false negative. If the email address is good, you certainly will go through, right? But approximately 1/8 that a bad email address might be luckily hashed to a bucket which has 1. So about 1/8 of the addresses not in S may get through. That is a false positive may occur. Again, false positive means that you say it's a good address, but in fact it's a bad address. So actually less than 1/8 because some actually maybe actually happen to each other. But we can actually make a more accurate calculation. All right. So we analyze this like throwing darts. Okay. How do we analyze it? We use this kind of example. This try to analyze the false positive. Let's consider that we are throwing n darts into n equal likely targets. We're throwing n darts. This n darts is like m email addresses. We hash them to the Boolean array, which has 8 billion bits. So there's this target is 8 billion targets because it is hashed to 8 billion positions. Like throwing this 1 billion email addresses into this 8 billion positions. If you throw it there, you turn that original 0 to be 1 in that particular bit position. So question is, what is the probability that a target get at least one dot? So the probability that target get at least one dot is what we want to estimate, because at least one dot means that these are those tend to be 1. So when a bad email address come in, it might be likely hit one of those. A quick estimate in this example is 1/8. Okay, but you'll see later that in a more accurate estimation is a bit less than 1/8. And in our case, again, we are our target, which is the position that we want to throw our dot. Our dot is a hash value of the email address, and our target is the bits or the bucket in the long bit array. So 1 billion dot throw to 8 billion bits in a Boolean array. That's the analogy over here. Okay, so we have m dots and n targets. Again, assuming m is less than n. All right, so m is like 1 billion dots, 1 billion email address, and n target is 8 billion bits, 8 billion position in that large Boolean array. So what is the probability that gets at least one dot, so that when we do actual checking of the spam email, the spam email may be by chance to hash into one of those Boolean array position which has 1. Okay, so this is sort of the false positive we want to estimate. Okay, and the estimation go like this. All right, this is the calculated result. Okay, let me just quickly explain it. 1 divided by n. This will be n target, right? There are n target. It's like 8 billion bits, right? And there's 1 over that, meaning that the probability target not hit any 1 dot. The target does not hit any 1 dot. This target hit 1 dot, right? Because you have this n target, right? 1 divided by n. 1 divided by n is that a target, this 1 target, right, was hit by 1 dot, right? Because you have that n target, so 1 divided by n is that of you. And if it doesn't hit with that, is 1 minus that. Okay, and you have to raise to the power of m. Okay, let me open this. This is probability not hit by dot. This is probability that at least 1 will be hit by the dot. Okay, and then this is just equivalent to m, because you can throw the dot m times. Okay, and you can throw the dot m times. Okay, so this is raised to the power of that. And finally, 1 minus that means that none of that will hit the target. Okay, so this is a calculation. 1 minus 1 divided by n to the power of m, and 1 minus that. This is similar thing that we have seen a couple of weeks ago. But these are the estimation that we have. But the key thing is the following. This value, we make it n times m divided by m, is because this inner box here, when n approach to large number, that is number of target, like 8 billion is a large number, 8 billion bits. This 8 billion, when it's a large number, this whole thing is equal to 1 divided by natural exponential, 2.71 something, right? 2.17 something. 1 divided by e, okay, is this value. Okay, and to the power mm. So this final thing is 1 minus e to the power of minus m divided by n. Okay, because this is 1 divided by e is e to the power of minus 1. So there's a minus value before this minus m divided by n, because this part is m divided by n. Okay, so this whole thing expressed to this 1, and that's why we can plot it. So to summarize, the fraction of 1s in the array of B is a probability of the false positive, because you turn all those position to be 1, right? And that probability is 1 minus e to the minus m divided by n. If we get, for example, 10 to the minus n dots, right, which means that you have m equal to 10 to the power 9, and you have 8 times 10 to the power 9 target. Okay, so we have n is the target, which is this value over here. N is this value. Then this estimation becomes the fraction of ones in this large array B. Is 1 minus e to the power of 1 divided by 8. This value is 0.1175, which is a bit less than 0.15, which is 1/8 in our example. Okay, rough estimate is 1/8. 1/8 of the large Boolean array, the position will be 1. Others will be zeros, right? But because multiple dots may be thrown into 1, that's why we do this estimate as this formula over here. So as a result, we will have this kind of error. So this error of false positive is still quite high. Can we reduce a false? Can we reduce this false positive? Can we reduce it? This is the last part I want to talk about for today's lecture. Sorry about this a bit long lecture. This error can be removed or improved with a well-known technique called Bloom filter. Okay. How do we do in the Bloom filter? The idea is that, okay, if you look into the example that we have, we are throwing 1 billion dots into 8 billion places. Okay, we are throwing 1 billion dots in 8 billion places, but we have this false positive of about 0.011 something. Okay, but what if the reason is because we only saw all of them once, and we saw all of them once, they happen to be in the same place. And the more you saw, the more chance you have them into the same place. Right? What if we just throw half of them, so they won't end up in the same place, but we do it twice? Then that actually will have a better situation, and that's the idea of Bloom filter. So in Bloom filter, we consider the following. Again, we have the sort of the dots, number of number of good email addresses as S, that is M, and the bucket size or number of the bits in the Boolean array is size of N. That's what we have, right? But let's do the following thing. We use not just one hash function. We use one hash function to hash it, just like throw the dot into this position. We use K of them. We use K independent hash function, H1 to HK. So we hash every one K times. Okay. So in that way, we set the B to be all 0, just like previously. But we hash each element as using each hash function H of I, so that we turn the particular position to be 1. But we do it K times, so I go from 1 to K. Okay. But in this way, we will not need to do that many dots. Okay. So in runtime, when a string element with a key of X arrive, we do it the same thing. We do it K times. In other words, a new address coming, we want to make sure it's not a spam, it's a good one. We don't test it once. Remember the false positive, because we tested one, it happened to be in this one of this position. 1/8 probability you have 1. Okay. Luckily, it may pass. Let's try not to do it once. Do it K times. In other words, you have to pass the K times of testing. Okay. So when a new element comes in, okay, if the hash function is 1 for all this K, then we declare it is a good one. Otherwise, any wrong one, we throw it away. So in other words, you imagine that you will reduce the false positive, because you will give that bad guy not just one chance. Luckily, he can go through. But make it multiple times, k times for that hash function. Okay. But the probability of hashing into the right place may increase. Okay. But he has to try it multiple times. So what function of the bit vector will be ones? Because we use a multiple hash function, you will turn or more ones, right? So this becomes throwing k times m dots in the n targets, right? Because we use k hash function, we hash this n target k times. So we are, instead of throwing m dots, we're throwing k times m dots. So the fraction of ones, just the same analysis as previously, the fraction of ones is e minus e times e minus 1 minus e times minus of m divided by m, but m now is expanded to be k times m. So in other words, fraction of ones actually will increase. Fraction of ones in this bit array of increase because we throw the dots not just m times, but k times m times. But we have k-independent hash function. So false positive means that you have to pass this k times. So probability that a false positive will be this to the power of k. And that number is expected to be actually smaller than 1 minus e to the minus m divided by n. In other words, k equal to 1. When k equal to a larger number will be better than k equal to 1. K equal to 1 is the previous example we have. Alright, so Bloom filter means that we filter it with multiple, in this example, k different hash function. Okay, and we actually see the following. If you use 1 million dots or 1 million email addresses and 8 billion bits in the bit array, okay, then we can see that when k equal to 1, we already have this false positive is 11.75%. But when k equal to 2, the false positive become 1 minus e, this value to the power of 2. That's already down to 4% or 5%, from about 12% down to 5%. And in fact, the number of hash function k and the false positive probability will go like this. So the optimum value is around 5 or 6. So k equal to about 5 or 6 is better. In fact, we can solve it, and it is 5.54. Okay, solving it means that you take this is the equation, the curve of the previous equation that we have. Okay, the previous equation here that we have. This equation, you try to solve for minimum. Right, just take derivative to be 0. You solve for that k equal to this value is about 5.54 with our example 1 billion and 8 billion for m and n. Okay, so for this, so far, is that okay? So for this, let me wrap up. The Bloom filter guarantee no false negative. Bloom filter equal to 1 is our original example, but usually we do it multiple times because we use a hash function k times. And 5.54 is the optimal situation. And we use a very limited memory because we need to keep track of all the keys, because keys already hash to a bit. That's all. And this is great for pre-processing before more expensive checks, right? And Google's Big Table or other system actually use this. It's suitable for hardware implementation in order to do a very quick hash function, and that can be done very effectively. Okay, so this is pretty much I want to go through. In fact, also my plan just kind of go through the first 3 algorithms. But the other algorithm, number 4, 5, 6, I have to expect you to study by yourself. The homework and exam may or may not include the later part, even though chance is lower. It's just a Bloom filter. Only through the filter, then it may filter out. But most of the time, that may not be in the exam or homework. But in any case, you can study them on your separate time. Okay? All right, sorry about this kind of a big hiccup of the tool and system. But if you have any questions, I'm here that we can talk to each other. The video I will put on the web for you to view as well. Okay?